Hello, adventurers, and welcome to the Hall of Names. A tree must walk, a name you need only speak. The hall keeps every name beside its meaning and asks for nothing but the word. The stair out of the balance hall does not climb, it opens, level, into a long room you can see the end of, and the end is quiet. There's no chart here. Where McCown spent 2 floors straightening a tree that would not stay straight, this hall is lined with shelves of nameplates, each plate with a beast's whole record engraved beside it, and the plates are already in order. Bone Spider, Cave Troll, Cinderbat, running off into the dark in a line so even it might have been ruled. Against the far wall stands a second, smaller shelf. Every kind of weakness listed exactly once, no matter how many beasts share it. The count is here, and for the first time in the stretch, his hands are empty. He is not straightening anything. On the last 2 floors, he says, I taught you to build the shelf, and then to keep it level. I will not make you build this one. He lays a hand flat on the nearest shelf, the way you rest a hand on something you trust. It is already built, better than I could have, and it never leans. I do not tend it. I only have to know the name. He speaks a name to the shelf. Lich, and the plate answers. The whole record there at once, with no dissent, no comparing, to no walk. The library tends it now. I am, at last, only using it. Look at the shelf and tell me what you do not see. You do not see me sorting it. I had these plates in the order the beasts were caught, goblin and wraith and skeleton, and yet the shelf reads top to bottom in clean alphabetical order, bone spider to wraith, because the shelf orders itself on every plate I set down. That is the thing you spent floor 9 earning from a walk, and floor 9.5 learning not to build by hand. A balanced tree, keeping order for free. The library handed it to me finished, and laid a second gift on top. Every plate has its meaning beside it, so I do not search for a name. I simply ask, and the answer is already there. A standard set for the names I only need to know are present, and a standard map for the names whose meaning I need. You will not write the shelf. You will write 6 small motions that use it, and you will be done by Friday, and you will have given up nothing that you needed. So up to this point, we've built containers on raw pointers. We've built a chain, a stack, a queue, a tree, a binary search tree, and the AVL bouncing that we deliberately stopped one step short of. The whole lesson of the balanced hall was an honest admission. Don't use your balance tree at the end of the day. Use something that has already been vetted, the standard set and standard map. So we're going to write some client code against using a set, a map, and a pair, and we do not have to implement the associative container. Okay. So the tree stretch was really 8 through 9.5. The Hall of Names begins with floors 10 and ends at floor 11. And it caches the promise the bard sang out on you. You stop building the shelves and start at last only to use them. So we're going to end up using the balance tree already in the box here. You get to use those in this one. So that's going to be great. Now, the standard set and standard map order in ascending, because they are our balance trees, is the connective tissue that this course draws. The Zybook describes the classes, but does not frame them as the balance tree from chapter 10. That's our own link there. And we're going to have a map, and understand that a map is a set with a value bolted on. So we're going to be able to answer with our set the question, is this name present, in a single count call without a loop. Now, using a map has a string and a monster, given this name, can we get the whole record using find? Okay. And then, of course, iterating on a map hands you standard pairs, and the key is a const. So we can walk a standard map with our standard range-based for loop in C++, and each step will yield us a pair that will give us a const key and a value. Okay. And then, of course, in C++ 17, it lets you unpack with structured bindings. Now, the key half is going to be the const side, and then the value, of course, will be the thing listed as value. Okay. And you can see here where we have our bestiary, which was an old school, and then we can see here when we start using our maps and our sets, how we can start using this key value index, where we can have our bestiary And then we can actually end up getting these sorted views by looking at things like by name or looking at weaknesses or the count of the weaknesses. So this is going to be really awesome here. And then, of course, whenever we use our bracket operators on our standard map, it is not a read. We use the M bracket key on a key that is missing, and our map default constructs a value and inserts it there. So a query that only meant to look silently actually grows the container. Okay, so if you ask accounts map how many fear thunder, and and there's nobody there, you'll actually end up getting a key value pair there, entry for that. Now, of course, we can ask with count or find, and then reserve the brackets just for keys you mean to set, and make our read-only query methods const. So then doing that cannot even compile. And we see here just understanding the reading versus the writing there and how that works. Okay, let's go ahead and get our VS Code pulled up here. Okay, here we are in our floor 10 project here. Now, let's go ahead and let's start by building our executable and seeing where the game field is at now. Okay, so when we roll in here, we'll notice we have a new self-test, which is our registry. So this will do our registry for our set, our map, and our pair harness. So let's go ahead and see where we're at here. And we got a lot of fails going on here, okay? So for 5 floors, we built containers on raw pointers. In the last 4, we made an honest deal. You'd stop one step short of a self-balancing tree because standard set and standard map are balanced trees and the library already gets it right. Today we're going to collect. The registry is just a thin wrapper that re-indexes McCown's bestiary into a standard map keyed by name, a standard set of distinct weaknesses, and a standard map of counts. But every method is stubbed, so our self-test fails 6 for 6 cleanly with a diagnostic on each line. Notice it fails, it doesn't crash, it doesn't refuse to build. That's our staircase. By the end of this floor, all 6 will be green. So today we're going to work on the first 2. We're going to open our registry header file under bestiary, and it's going to be time to get to work here. Okay. So our first thing we'll want to do is go to our private members for our registry class down here. And now before we write anything, let's get down here. Okay, so down here at the very bottom, we see our private members and the constructor. So you see here we have our, well, let's first, everything's provided here. We have 3 containers, a standard map from name to the whole monster record there. That's the key value index, the thing floor 9's BST did in one declaration. A standard set of strings for the distinct weaknesses. The raw data has fire 6 times, holy 3 times. A set collapses those duplicates and keeps them sorted. And we have a standard map from weakness to an int count. Now the constructor is also provided. And with that one, which I need to scroll us up here. On our registry here. Okay, so up here we also have an explicit registry as well. Now, so for our constructor, it actually walks the bestiary in file order and calls index once per monster. Okay, that's the hook there. Whatever index does to the 3 containers, it does 15 times. Right now our index is empty, so the loop runs and nothing happens. Size is 0, and that's the self-test first failure. So what we need to do, first of all, is make index do its job. So let's go find our index stub, which is right here, starting on line 113. And the body here, I need to say by name, m.name, and then say, this is brackets, m.name, equals M, and I'll say weaknesses dot insert M dot weakness counts M dot weakness plus equals 1. Okay, so it's really just 3 lines, 1 per container. First, our by name bracket M dot name equals M, we file the record under its name. Here, the bracket is exactly right. We mean to create or update this entry. That's what the insert or update is. Second, our weakness dot insert of M dot weakness, we push the weakness into the set. If it's already there, the set quietly ignores it. That's the deduplication happening for us for free. Third, our weakness counts bracket M dot weakness plus equals 1. We're going to bump our tally up. And notice the first time we see fire, that key doesn't exist yet. So the bracket default constructs an int, which is 0, and then we add 1. That's the bracket's insert on missing behavior working for us, because here we genuinely want to create the key. Hold that thought. In the next video, we're going to meet a method where the same behavior is a disaster. But for now, 3 containers, 3 lines, all populated. Now, we will also go to our nose stub. And we need to say bool. Well, actually, we just need to return by name dot count name greater than 0. Okay. So 1 line, our by name dot count of name greater than 0. On a standard map, every key is unique. So count returns either 0 or 1. It's a yes/no membership question. No loop. We do not walk the bestiary asking, is this you? Is this you? 15 times. We ask the map once and it descends in its balanced tree in log of n and answers. That's really the beat of the day. Is the name here is a single call against a structure that's built to answer it. You could also write find of name not equal to end. That's the same thing, same cost. Count reads cleaner for a pure yes/no question, though. This method is const because asking a question shouldn't change the answer, and count never inserts, so it's safe inside a const method. So let's go ahead and build this here. Perfect. And now our first 2 are good to go. So phases 1 and 2 are green. Phase 1 proves index populated all 3. Size 5, 3 distinct weaknesses, and the count of holy is 3. Okay. Phase 2 proves nose finds lich and correctly does not find the drake. Okay. Phases 3 through 6 still fail. Those are in the next video and the third one. And now we can see if we can run. You notice we also have a no command. If you look up here, we also have our nose command. Notice it says, does the registry standard map know this name? So we can say nose lich. The count knows the lich. Nose drake. The count does not know the drake. I could say weaknesses. You can see here, right now we have 6 distinct weaknesses and 0 monsters. So nose works on the real bestiary. So you notice here, the real moment right here to look at is in weaknesses, we have 6 distinct kinds here. Which actually ours, hold up, let's see here. Okay, so notice that these are alphabetical order here. Right now it's counting 0. I kind of got ahead of myself. We're going to fix that for the next video. What happens on the back end is that it comes from count weaknesses, which is still stubbed to 0 until the next video. So for right now, it's going to read 0 on all of those. So we will be fixing that in the next video. So I hope this was helpful. And I'm ready to see you in the next one. I'll see you soon, adventurers. Bye-bye.